Hello and welcome back. Recall in previous videos we were able to make these connections between position, velocity, acceleration, and time, specifically looking at graphs and trying to be able to extract information about quantities from other quantities graphs. So these four relationships are going to be very important in understanding, being able to use and extract information from. So recall that the velocity is the rise over run, or the slope, on the position versus time graph. The acceleration is the rise over run, or the slope, on the velocity versus time graph. The displacement is the area under the curve on the velocity versus time graph. And remember, if it's area that's above the time axis, that's going to correspond to a positive delta x, or positive area. If it's area below the time axis, then that's going to correspond to a negative displacement, or negative area under the curve. The change in an object's velocity is just the area under the curve on the acceleration versus time graph. And we're going to use those four pieces of information to try and draw the other graphs just given one. So let's start off with just looking at a velocity versus time graph. So here's a graph for velocity versus time. And let's say that this graph looks something like this. So there's our velocity versus time graph, and let's just see if we can translate this to making sense by thinking about a car moving or something like that, okay? Remember, when we're graphing, we're only representing motion in one dimension because this is just a two-dimensional graph. If we wanted to represent velocity, motion, acceleration in in two dimensions, then we would need to have a third dimension here, an x and a y and a time axis. Very hard to draw on a two-dimensional surface. We won't be worrying about anything other than one dimension. So this is going to translate to either motion in the positive direction or motion in the negative direction. So what happens? Well, the car starts off, using a car as an example, with a velocity of 0. In other words, right here at time t equals 0, the velocity is 0. And what happens as time starts ticking off? Well, the velocity is becoming more and more and more negative and getting larger, right? So this translates to motion in the negative direction, increasing in speed until some maximum speed is reached in the negative direction. And now continuing to move in the negative direction, because again, this is all underneath the time axis, so that corresponds to the negative direction. The object is slowing down, continuing to move in the negative direction, slowing down until it reaches a velocity of 0 again at the end of its interval. So now, can we draw the position versus time graph knowing this velocity versus time graph looks like this? Going from velocity versus time to position versus time graph, we need just one extra piece of information, and that is, where did the object start? In other words, give me the position at time t equals 0 so that I can draw the exact graph. The shape will be the same, but where the time t equals 0 intersects the x-axis is going to be totally dependent on the position at time t equals 0. So we need an extra piece of information there to get it exactly right. So let's go ahead and draw the position versus time graph up here. So here is position versus time, and you can see that we want to line up, and that's why I'm drawing it like this. We want to line up these graphs so that we have these transitions at the proper time. So here's my position versus time graph, and again, this is a position that is negative with respect to the origin, and this is positions that are positive with respect to the origin. So negative below the time axis, positive above the time axis. And I'm going to give the extra piece of information that at t equals 0, x equals 0. Another way to say all of this, an equivalent way to say that, is x naught equals 0. Remember, that little naught sign keeps track of initial. So it says initial position is 0. So I know I start off right here. Okay. Now, how do I draw the position versus time graph knowing the velocity versus time graph? Well, I do it by using this first piece of information. I know that the velocity is the slope on the position versus time graph. So what I'm being given here is the value of the slope on the position versus time graph at any time that I want. So what is the slope on the position versus time graph at t equals 0, where the slope is the velocity and it has a value of 0. So there's no slope at time t equals 0. So that I have a horizontal line that's tangent to the curve. Now what happens to the slope on the position versus time graph as time goes on? The slope is getting more and more and more negative, increasing to some maximum negative value. So the slope should be maximum and negative right here. And so that's going to be a maximum negative tangent line. And it's not an infinite tangent line like I've drawn. So let's represent it a little bit better. There we go. So there's the tangent line. That's a negative large slope. And remember, I'm going to just write over here so you remember, this is the slope on x versus t, right? So that's what velocity means. So as I go through the second part of the interval, now my slope on the position versus time graph should be remaining negative but becoming more and more shallow until it reaches a slope of 0 at the end of the interval. So it wants to remain negative, but then it's going to end up with a slope of 0, which is going to translate to a horizontal line. So now let's go ahead and fill in the rest. And that's what the position versus time graph is going to look like. So you can see now, if I instead just had the position versus time graph and I want to draw the velocity versus time graph, well, I would just simply look at the slopes on the different points in time on my position versus time graph. So at position time t equals 0, I should have a slope of 0. That means my velocity is 0 there. Now what happens in this first interval is I move from 0 to the halfway point interval. Well, my slope is becoming more and more negative, maximum negative right at the halfway point. All right, so that means the velocity more and more negative, maximum negative at the halfway point. Now what happens in the second part of the interval? Well, my slope remains negative, but it's becoming shallower and shallower and shallower until it hits 0. That means the velocity remains negative, but becoming smaller and smaller until it reaches a value of 0. So you see how you can go both ways. Now notice that this particular condition defined where I start. If instead I had said x naught equals 10 meters or something like that, then I would have started up here, but I still would have had this same shape. So it just would have been shifted up. Okay, the last graph that I want to draw is the final one. Here is the acceleration versus time. So up here, positive accelerations, down here, negative accelerations. And so when I look at my velocity versus time graph, the slope on the velocity versus time graph is the value of the acceleration. Okay, so tell me about the slope from 0 to the halfway time interval. Well, you can see that the slope is constant and negative. So now substitute word slope for acceleration. So the acceleration is constant and negative. So that corresponds to a constant negative. A constant is just a horizontal line. So there's my constant negative. Now what about the second half of the interval on the velocity versus time graph? Well, you can see that the second half of the interval is going to be a slope that is again constant, but this is a constant positive slope. So for the second half of the interval, I'm up here and I have some constant positive slope. So that's how my acceleration versus time graph looks with respect to this velocity versus time graph. So this is the set of graphs that define the position versus time, velocity versus time, acceleration versus time, just being given the one velocity versus time graph to work off of. Next time, what we'll do for more practice is we'll start with an acceleration versus time graph, and we'll see if we can work backward. And when we do that, we're not only going to need to know the initial position of the object, but we're also going to need to know the initial velocity of the object to be able to go from acceleration to velocity and then go from velocity to time. So we'll do that in the next video.